皆様大変お待たせいたしました。アンジェリカ先生が電話経由で入っていただくことになりましたので、ちょっと先生のお顔をご覧いただくことはできないんですけれども、この状態で本日講演会を開始させていただきます。本当にお待たせしてしまって申し訳ありませんでした。はい。
Thank you very much, everyone, for waiting for a long time till the opening of today's session. Since some technical trouble, the Dr. Zidek has had many trouble to join the system. However, finally, she is now joining with us. Although it's not through telephone system, but now we'd love to see her presentation, although we cannot see her face. But now I'd like to start today's session.
で、講演の資料はチャットで表示されている URL からダウンロードしてください。
Regarding the presentation material for today's presentation, please download the material from the URL that you can find in the chat box.
すみません、通訳さん、ちょっとハウスキーピングアナウンスメントの部分は通訳不要ということでお願いできますでしょうか。
Now, let me explain the housekeeping announcements, and there will be no interpretation for this part.
講演の動画は後日国民会議のホームページにアップする予定ですので、本日の講演の録音、録画、スクリーンショットなどでの撮影は固くお断りいたします。講演後に質疑応答の時間を設ける予定ですので、質問はウェビナーの画面下の Q&A からお送りください。すべての質問にお答えできない可能性があることはご了承ください。ウェビナー終了後にアンケートが表示されます。今後の講演会の改善のため、どうぞご協力ください。では、早速、講演会を開始したいと思います。化学物質リスク評価におけるバイオモニタリングデータの使い方について、カナダ政府保健省のアンジェリカ・ジーデック博士にお話しいただきます。では、アンジェリカさん、よろしくお願いいたします。
Hello, and welcome to the seminar on the use of biomonitoring data in chemical risk assessments. I would also like to thank the organizers for giving me the opportunity to present here today and to discuss one of my favorite topics within the world of human health chemical risk assessment. First, I would like to start the presentation with a bit of a background on the chemicals management plan here in Canada, then touch on some key considerations when deciding when and how to use biomonitoring data for chemical risk assessment. And finally, I'll present a few case studies at the end that look at different approaches for using data, and closing with thoughts on limitations and uncertainties when interpreting human biomonitoring data. For some background, Canada's Chemicals Management Plan was launched in 2006 with the aim of advancing and improving the management of chemicals to safeguard the health of Canadians. As the figure in the top right-hand corner depicts, there are key drivers in the cycle of research, risk assessment, risk management, and compliance and enforcement. Monitoring and surveillance plays a key role in informing chemical priorities and data used to assess and manage chemicals. More specifically, human biomonitoring data support a number of legislative acts by providing evidence of exposure for risk assessment, tracking the effectiveness of risk management actions, and helping to identify new emerging chemical priorities for future risk assessment. How can biomonitoring data be used in chemical risk assessment? Human biomonitoring data can be used both qualitatively and quantitatively, though the latter is seen less often. So qualitative uses can include looking at trends or patterns. For example, do females have higher concentrations? Are there certain age groups with certain concentrations? And how do exposures differ when comparing urban and rural populations or other countries? Another qualitative example is examining cross-sectional health surveys or prospective or retrospective epidemiology studies and looking for potential associations or correlations with a given health outcome. So an example here is when looking at an inorganic chemical called selenium, which is one of the case studies I will present later, we looked for potential associations with selenium exposure and type 2 diabetes. And you can also use human biomonitoring data to see if substances are low concern based on an absence of detection in surveys, assuming that your biomarker is correct. Now moving over to the quantitative blue box, quantitative uses takes the data further and actually converts measured concentrations in urine or blood to an internal dose. And I will provide some examples in the two case studies where we look at quantitative extrapolation of human biomonitoring data. Next slide. There are a number of considerations that should be examined when evaluating whether and how human biomonitoring data can be incorporated into human health risk assessment, including adequacy of the biomarker, quality of the data, appropriateness of the data set, and the approach to be used for interpreting the data. The next few slides will go into more detail of each of these specific considerations. Next slide. So as a regulator and within the context of Canada's Chemicals Management Plan, we use a number of considerations before incorporating human biomonitoring data in our chemical risk assessments. One of the first steps is examining the adequacy of the biomarker, which I will get into in the following slide. I will also look at whether the study is of sufficient quality, the appropriateness of the data set, and any extrapolations being used for your population of interest. And finally, the approach you use when you interpret the data, including qualitative and quantitative applications. The use of human biomonitoring data in regulatory risk assessment typically starts with an evaluation of whether the biomarker of exposure is specific and sensitive, such that the concentration measured reflects exposure to the substance of interest. So the biomarker of exposure is the chemical or its metabolite that is measured in a compartment or a biological matrix in an organism. So this compartment or biological matrix can be blood or urine or breast milk. Questions for considering and determining the adequacy include, can the biomarker be distinguished from other chemicals? In other words, is it specific and sensitive? And most importantly, are the pharmacokinetics well described? And this means the absorption, distribution, metabolism, and excretion profile. You will need to understand what the extent of metabolism of that chemical is in the body. How long does it stay in the body, or what is its half-life? What amount is excreted in the urine versus feces? And which is the appropriate matrix to be looking at? Is it better to look at it in urine or blood? So chemicals that are semi-volatile or hydrophilic that have short half-lives, such as phthalates and triclosan, are better suited for measurement in urine as opposed to blood. Next slide. An important consideration is evaluating the quality of the human biomonitoring study. This includes looking at analytical sensitivity of your analyte. So an important consideration is the analytical limit of detection or limit of quantification. If the limit of detection is too high, you might not be able to find the chemical in urine or blood. If there's no information in this study on the limit of detection or the limit of quantification, that is considered a major limitation in being able to use the data for risk assessment or regulatory decision making. The study design, including the types of samples collected, may affect how human biomonitoring data can be applied in human health risk assessment. For example, serial urine collection, so those are a collection over 24 hours without any missed samples, that is preferred over a spot urine sample, which is just one sample for the whole day. But it's very rare to get serial urine sample collections. The timing of the sample collection is also especially important and sensitive to substances with a short half-life. Another type of sample collection is pooled samples, where multiple individual urine or blood samples are all combined into one big sample. There are limitations, though, because this reduces your ability to interpret it. However, this method only provides a measure of average exposure in a population and has limited ability to estimate the upper tails of the distribution. So you may ultimately miss out on highly exposed subpopulations. The next consideration is representativeness of the data in terms of the subpopulations examined as well as the geographic location. An important question to ask is not necessarily which subpopulations were examined, rather which subpopulations were not examined. Exclusion of certain geographic regions or subpopulations may reduce the comprehensiveness or completeness of a given data set, as well as limit the ability to ascertain potential risk issues in susceptible populations. No worries. For example, if you collect samples across a country, but the substance is used primarily in the mining industry, you may not be capturing exposures that could be higher where mining activity is highest. Consideration should also be given to the sample size of a given study. Generally, larger studies provide more confidence in terms of the distribution of measured concentrations. However, this depends on the subpopulation targeted. For larger national surveys, consideration should be given to the use of general population concentrations versus measurements in specific, smaller subpopulations. Often, national surveys may be limited in sampling infants and children. Sample size for a specific age group or gender should also be examined if exposure is expected to be higher in a certain age group or gender, or a group that's more sensitive in terms of the toxicological effect. And lastly, the age of the study should be examined to see whether exposures captured are still relevant, given the ever-changing global market and use of substances in a variety of products that could change from decade to decade. Looking at the appropriateness of the data set, for geography, when we don't have data in Canada, we may look to the United States or to Europe to see if they have human biomonitoring data available. However, we need to consider if these other countries would have similar exposures. Some questions to ask would be, are the diets similar between the different countries? Do other countries have the same products that the chemical may be present in? Are there differences in manufacturing or industrial activities? Time trends are also important. If data is only available for 1 or 2 years, it may be difficult to really confirm whether exposures are truly increasing or decreasing. It is also important to really understand what is your subpopulation of interest, who truly has the highest exposures or the greatest susceptibility to a chemical in terms of health effects. Some studies may not examine infants or toddlers or even younger children due to constraints with collecting samples from these subpopulations. Care needs to be taken when drawing generalizations to these younger age groups. It may also be important to look a little deeper into the data to pull out factors that may influence exposure levels, such as gender, socioeconomic differences, or occupation. Lastly, timing may be critical. For risk assessments, it can take several years to complete a risk assessment, only to have new data become available at the time of publication. Human biomonitoring data can be interpreted using several different methods, including using reverse dosimetry or forward dosimetry methods to transform data in order to compare exposure with health effects. In the absence of epidata or sufficient data to directly compare concentrations with health points, reverse or forward dosimetry has been used to transform human biomonitoring data or health endpoints to facilitate interpretation of the data. So for reverse dosimetry, concentrations in urine or blood are what we consider internal body measurements, and we would convert these to an external dose using kinetic data to estimate what that external dose was that resulted in the internal dose. I'll present a case study on this in the next few slides. In comparison, for forward dosimetry, you start with the external dose that you know will cause a health effect, and you convert that into an internal dose in blood or urine. Forward dosimetry is applied in the derivation of what's called a biomonitoring equivalent, or a guidance value. In the annex of this presentation, I've provided links to biomonitoring equivalents as well as guidance values developed by Germany, and you can sort of look at all of these guidance values at the end. So finally, for direct comparison, if your concentration in blood or urine is associated with a health effect that is known and understood, you can compare it directly with the health endpoint. For example, for lead, you can have your concentration in blood and compare with associated causality established for neurodevelopmental effects. Now I'm on slide 12. As I mentioned in the previous slide, reverse dosimetry works backwards. So moving from the right of the slide with an internal dose or concentration in blood or urine, and trying to reconstruct the exposure to estimate what the external exposure was that contributed to the internal dose. This requires a solid understanding of the pharmacokinetics of the chemical. In other words, how is it absorbed, distributed, metabolized, and eliminated by the body? Next slide. So now on slide 13. For our first case study, I wanted to showcase a chemical called triclosan. What is unique about triclosan is the absolute completeness in terms of ages covered in the available human biomonitoring data. There are very few chemicals that have biomonitoring data available to cover the fetus, infants, toddlers, children, adolescents, pregnant women, adults, and seniors. So now on slide 14, looking more closely at the specifics of triclosan, biomarkers were available that showed triclosan had a short half-life, which means it's not around in urine very long. It also had supporting pharmacokinetic data based on oral dosing in human studies. So intake or internal estimates, your internal dose, was estimated from spot urine concentrations, and this required some corrections, and a reverse dosimetry approach was used to work backwards from an internal measurement to an external dose. We also had to make adjustments to the spot urine samples to correct for hydration status using specific gravity, and further conversions were used to adjust spot concentrations into a 24-hour daily dose. So this required information on urine volumes for 24-hour urine volume for each age group. We also needed to identify the fraction excreted in urine. So if you ingested 1 milligram of triclosan as a pill, we found out that only 20 to 50% would be eliminated via urine. So your sample does not include all of the exposure that you were exposed to from the original external dose. And finally, extra care was taken to fully understand exposures in infants and toddlers, since the sample size for these age groups was much smaller, and to be protective of human health for this vulnerable age group. So separate exposure estimates were made for exposure from breast milk, mouthing plastic toys that may contain triclosan, and accidental ingestion of dust from crawling. And this gave us a more complete picture of the possible sources of exposure for infants and toddlers. Next slide. So slide 15. Here we can see the various levels of exposure following dose reconstruction. The y-axis represents the external dose in micrograms per kilogram body weight per day. On the x-axis are the various biomonitoring studies. As you can see, the studies with the highest estimated exposures were for pregnant females, followed closely by adults 20 to 59 years old. This is not surprising given triclosan is used in many personal care products. What I also wanted to highlight here is the choice of metric. The 95th percentile exposure estimate was selected as opposed to the geometric mean, as it was felt this was more appropriate given the short half-life in urine and the use of spot samples, which may not have captured all the exposures in a day or sampled at the right time. And finally, the blue line at the top shows the level at which risk concerns would emerge. So as you can see, all estimates of daily exposure were far below the value of 84 micrograms per kilogram body weight per day. Next slide. So now on slide 16, moving on to the second case study, we will look at forward dosimetry, where we start on the left side of the slide. So the green circle depicts an external dose. For example, if you took a pill, and this is the dose in a human pharmacokinetic study to understand how the chemical is eliminated from the body. This external dose is converted, correcting for absorption, metabolism, distribution, and elimination, into an internal exposure, or your biomarker concentration. So now on slide 17. So for the second case study, I will be talking about selenium, which is an essential element present in food, drinking water, and other sources of exposure, including vitamins and food. Selenium has been measured in a variety of media, and for this case study, we compare health effects, illustrating the forward dosimetry approach. So specifically, comparisons are made between a whole blood concentration to a biomonitoring equivalent. And to do this, the health effect, which is selenosis, was converted to an internal dose so that we can compare the blood concentration available in human biomonitoring studies. So again, the pharmacokinetic data and epidemiological studies are used to establish and derive a quantitative relationship between blood concentrations and dosing. So now looking at slide 18, the Institute of Medicine previously established a tolerable upper intake level for selenium at 400 micrograms per day based on epi-studies where associations with blood and intake resulted in selenosis. So this allowed a biomonitoring equivalent to be established, or a whole blood equivalent, at 480 micrograms per liter. So any value above this would indicate potential risk issues. Next slide. So on slide 19, you can see whole blood concentrations, or the internal dose, in micrograms per liter on the y-axis, and the various biomonitoring studies on the x-axis, showing both median and 95th percentile blood concentrations. The studies included national Canadian data from 3 to 79 years old, as well as data from Indigenous populations. As you can see, it is the latter subpopulation that had the highest selenium concentrations, including the highest levels in children from Nunavik. The red line on the graph indicates the biomonitoring or blood equivalent based on the tolerable upper intake level, which is exceeded when comparing the 95th percentile blood concentrations in Indigenous populations. This is concerning. The blue line at the top depicts where selenosis cases were observed in select human populations, which is also exceeded. And finally, the green line at the bottom shows the estimated average requirement, given selenium is an essential element. It's essential to our diet. So based on blood concentrations in the studies, there are no deficiencies noted in any subpopulation. So slide 20. The use of human biomonitoring guidance values in screening assessments can be useful in managing regulatory efforts. Where biomonitoring data are close to or exceeding a guidance value, more work needs to be done to better understand potential risks. So this table provides examples of guidance values used or available for a variety of metals. But while a quick comparison is fairly straightforward, it's still important to consider whether your data set is of high enough quality and that the exposures you're trying to examine would be captured by the data. In addition, data in infants and young children may not be available, or the guidance value may not always be appropriate for extrapolation to younger children or infants if the data suggests metabolic differences when compared to adults. Next slide. So slide 21, before I close, I wanted to leave you with some thoughts on limitations and uncertainties that should be acknowledged, as with any type of data that is considered when attempting to evaluate human health risk. In terms of limitations with the use of human biomonitoring data in human health risk assessment, there are only a few hundred chemicals that have been measured in various matrices, but tens of thousands of chemicals in existence. While you may have a chemical measured in urine or blood, it does not necessarily equate to an adverse health effect in that subpopulation. At the same time, absence of a chemical measured in urine or blood does not mean that exposure did not occur. For example, the biomarker may not be appropriate or specific, or the timing of the sampling was incorrect, or perhaps the limit of detection was too high to be able to detect exposures. Human biomonitoring data alone cannot determine the main source or all the sources of exposure, nor the route of exposure. There are also limitations in determining the relevance and translation of occupational exposure to other non-occupationally exposed populations. And one of the biggest limitations of being able to use human biomonitoring data is a lack of knowledge or understanding of the chemical-specific pharmacokinetics. And lastly, there are often limited or no human biomonitoring data for infants and toddlers, so it's important not to forget about this important subpopulation. Next slide. So looking at slide 22, in terms of uncertainties, hazard or health effects data are typically based on a dose versus the internal exposure you are trying to compare it to from human biomonitoring data. To be able to use human biomonitoring data in risk characterization, these two need to be linked, which can be challenging and may introduce uncertainties. There are also uncertainties associated with the assumption of steady state exposure when interpreting your data. It's possible you may have missed key exposure events and thus underestimated exposures. And finally, there are a number of assumptions that are made to convert a spot urine sample to a 24-hour dose. This includes corrections that rely on defaults that introduce their own errors and uncertainties, such as urine volume and creatinine excretion. You also need to assume a certain fraction is excreted in urine, but this value is not always exact nor constant across age groups and for all routes of exposure. Lastly, when you do not have infant or toddler data, corrections for urinary excretion are based on adult data or factors which may not always be appropriate, and this introduces uncertainties into your exposures and ultimately your risk estimates. Next slide. I'm happy to take any questions.